Our next induction example takes us back to the mathematical kindergarten. We're going to prove this very basic fact that any non-empty finite set of integers has a maximum. And just as a reminder, a maximum of a set S of numbers means an element S in S such that every T in S satisfies S greater or equal T. So it has to be in S, and every element of S has to be less or equal to it. So it has to be greater or equal to everything in S. And it's also known as largest element. And when I say numbers here, it could be integers, it could be rational numbers, real numbers. I'm going to say real numbers because it's the most general case in a way. It cannot be complex numbers, of course, because they don't have inequalities. So this is a very basic fact. You can use it without proof in any competition. You don't even have to cite it. I'm just using it as an example because it illustrates something about induction. And by the way, it is very easy to see that any set of real numbers has at most one maximum. If you haven't seen this argument, it's a very nice little exercise. But so of course not any set of real numbers has a maximum. Some just don't. So the set Z itself has no maximum because integers can be arbitrarily large. You can always go further up. But non-empty finite sets have a maximum. So why? The idea that this illustrates is you don't need to have an n in the statement in order to prove it by induction. So why? Well, a non-empty finite set must have n elements for some positive integer n. Positive because non-empty, integer because finite. So thus we need to prove the following claim. Claim 1, let n be a positive integer, then any n element set of integers has a maximum. So now we have restated our claim in a way that does contain an n, and now of course it's clear that you should be proving this by induction on n, because how else are you going to prove such a statement? So proof of claim 1, induct on n. The word induct is just short for apply induction. Okay, let's actually do it. Base case, we must show that any one element set of integers has a maximum. This is clear because its one element is also its maximum. Induction step, let m be a positive integer. Assume as the induction hypothesis, again, let me just say SIH, that any m element set of integers has a maximum. We must prove that any m plus 1 element set of integers has a maximum. So let S be an m plus 1 element set of integers. What can you do with an m plus 1 element set? You can pick some element of it and throw it away, and then you get an m element set. So pick any S and S. And to be fully precise, why can we do this? Why is there such an element? Well, we can do this because S is non-empty. After all, S is an m plus 1 element set, so its size is m plus 1, which is at least 1, which is bigger than 0, so S is non-empty. This is stupid, this is obvious, but somehow if you don't think about it every once in a while, you will actually get bitten by a contradiction. So don't underestimate the value of such arguments. Okay, so then the set S without S is an m element set of integers. So by the induction hypothesis, it has a maximum, and let me call this maximum T. And now I claim that S also has a maximum, namely, well, I have to pick from S and T basically. The idea is that when I reintroduce the element S back, either t stays the maximum, or if not, then s beats it. So if t is greater or equal to s, then t is the maximum of s, and if t is less than s, then s is the maximum. Check this if you don't believe me. So we're done. Again, the induction step is thus complete. And therefore, our exercise is also solved. So just as a remark, integers, so this has little to do with integers. We can replace integers by rational numbers or real numbers, and it's still true by the same argument. Also, we can replace maximum by minimum. There is a total symmetry here between, of course, we would have to turn all the inequality signs around.